All right. So recording starts now. Test is on Friday. You get it back on Wednesday. Good thing you were all here, right? Good thing some of you were on Zoom. If we just showed up, ask your neighbors what we talked about for the last 11 minutes. Sorry about that. I'm actually not sorry that I record every lecture and do it on Zoom. Like that is just extra work for me, okay? At some point, I'm going to say no, but I'm really not because it does help the few people. And the people who slack off because of it, it pisses me off, but I'm helping out the people who actually have real situations and use it. So I care about the ones who need the help, not the slackers. But I care about you too if you're a slacker. And you know when you're a slacker, right? So if molarity is moles per liter and a millimole is a thousandth of a mole, what would be a thousandth of a liter? Honey? A thousandth of a liter would be a what? So there's 1,000 mils in 1 liter. So 1,000th of a liter is 1 milliliter. Everybody see that? So what we can do is instead of saying that molarity equals moles per liter, if we divide the top by 1,000 and we divide the bottom by 1,000, is the molarity still going to have the same ratio? What do we think? It will, right? It'll be the same molarity. So what I do is, especially for these kind of problems, because we're always working with like 0.0025 moles, 0.0050 moles, I say that a molar is equal to a millimole per milliliter. And let me show you why that will be nice, okay? So I'm going to make my own. This is the stoichiometry table, right? So we're calculating the pH after 5 milliliters of NaOH is being added. All right? So we have 25 milliliters of, I'm just going to write it as HA, but the HA is representing HCHO2. And the nice thing is, so when we calculated this thing over here, we did 25 mils, we converted it into liters, and now we could use the molarity of 0.10 moles per liter, and that would have gave us 250 divided by 1,000 would give us 0.025 times 0.1 would give us this value 0.00250 moles. Okay? What happens if we use millimolar? What is the millimolar of 0.10 molar? What can we rewrite that as? Analia? What can we rewrite molarity as in terms of millimoles and milliliters? It's going to be exactly the same as moles per liter. So when we said that this value, 0.1 moles per liter, 0.1 molar equals 0.100 moles per liter, that means that it equals 0.100 millimoles per milliliter. And what's nice about this is now we can do 0.10 millimoles per milliliter, and we didn't have to do this extra step of converting that we saw over here, converting it into liters, right? 25 times 0.1 equals how much? 2.5 millimoles. Is 2.5 millimoles the same as this? Remember, it's 1,000th of the value. 1, 2, 3. When we move it over to 3, it gives us 2.5. So basically, we're going to calculate in terms of millimoles. And I would rather do something with a value like 2.5 than 0.0025. Okay? If you like doing it with those decimals, feel free to do it. But I'm going to show stuff in millimoles. Okay? So now, when I do my table, we have hydroxide plus our HA. We're starting off with 2.5 millimoles of HA. Now, HA is a weak acid. How many moles of strong base did we add? Let's change color here. We had 5 milliliters because we're adding 5 mils of NaOH. Everybody see that? So we have our, and you might be like, why am I leaving off all the decimals? 5.00 and 5 is the exact same value. One has more sig figs. I would always go back and figure out sig figs at the end. I don't always like punch into my calculator 5.00. I know it's the same as punching in 5, okay? I would go back and check my sig figs, in this class, sig figs are not that important, especially when you're submitting it on Canvas, okay? So we have 5 milliliters, and this is 0.100 millimoles of NaOH per, and when it's NaOH, can we just think of it as OH minus? Why can we think of it as OH minus, Amanda? Why is NaOH equal to OH minus? So when I say we're adding NaOH, you can write NaOH every time, or you can just think of NaOH as OH minus. Why do we think of it as OH minus? Basically, what I'm trying to say is anytime we have a Na in anything on this chapters, get rid of the Na and a plus, and whatever's left over is the OH, and we have to give it a minus. And that's the thing that's reacting, okay, is the OH minus. The Na plus just floating around, doing nothing, sitting in here, playing on its phone, not paying attention. Who am I talking about? Could be anyone. If you're guilty, you know it's you, right? Your laptops are just like phones also when you're playing stuff on your laptop, okay? So it's 0.100 millimoles per milliliter. How many millimoles of OH minus am I adding? 5 times 0.1 gives us 0.5 millimoles of OH minus. So we can say the addition is we're adding in 0.5 millimoles. That is going to subtract 0.5 millimoles from this because, as we said earlier, the OH minus grabs the H from the HA, right? So HA goes from 2.5 down to 2 millimoles of HA is left. What happens though is we can have A minus in here, and that is going to become this 0.5 moles negates 0.5 moles of HA, but it creates 0.5 millimoles of A minus. So notice how we still have a total amount. So we started off with 2.5 millimoles of HA. We now have 2 moles of HA and 0.5 moles of A minus. The total overall quantity of A is still 2.5 millimoles, right? We didn't lose any A minus in the solution, and we have to consider A minus because it is the conjugate of a weak base based on the fact that it is not a strong acid, okay? So now how do we solve for this problem at this point? Kayla, what do we do? So we could do an ice table, but in this situation, do we have acid and base? What do we do when we have acid and base, Alondra? What's the easier formula to use than the ice table? So you can plug it into the Henderson-Hasselbalch, okay? If those of you are not sure when to use the Henderson-Hasselbalch, you can always do the ice table and it will always work. I think it's a little bit more labor intensive since it's a take-home exam. Do it both ways. Verify that it works both ways, okay? You want to do well on this exam because we have this and a final left, couple little homework assignments, and that's about it. So the Henderson-Hasselbalch is pH equals pK plus the log of base over acid. It's supposed to be in concentration. Can I just use the moles in this situation over here? What do we think, Nate? Is it okay to use moles and not molarity? Yes or no? Yes, it is okay. Why is it okay, Danny? Because it's just a ratio, right? If you have a ratio of concentrations, if they're both in the same solution and you know the moles, if we do 0.5 divided by the total volume, which is 30 mils, and 2 divided by 30 mils, let's do a quick off-the-cuff calculation. Let's see what happens when we do 0.5 divided by 2, okay? And now let's do it 0.5 divided by 30 over 2.0 divided by 30. So what is 0.5 divided by 2? Is that 0.25? What is 0.5 divided by 30? I can tell you what it is. It's 0.25. But just to verify, what's 0.5 divided by 30? Anybody? 0.016. And what is 2 divided by 30? 0.06. Okay, now if you divide those out, it should equal 0.25. Okay. I mean, and it just depends on the repeating nature. They're going to be a little bit off. So really, you're using better math by not dividing both by 30, because when you have like this repeating 6, does 0.016 divided by 0.066 equal roughly 0.25? Yeah. Pretty much, right? So you can just use the moles and not the molarity in this case. See how I did it over here with millimoles? You see how it's 2.5 divided by 0.5, giving us 2, plus 0.5 gives us 0.5, versus 0.0025 minus 0.0005 gives us 0.002 and 0.0005. It's up to you which one you want to use. I prefer to use millimoles. Do we understand how to use millimoles? That's going to make your life easier. So that was equal to 0.25. The log of 0.25 is negative 0.6. The pKa, where did we get the pKa from this? We would have looked up the Ka of this weak acid here. So on the exam, I'm not going to tell you which acid it is, because you could just look it up on AI. Like I said, I'm going to put in something random so it's not look upable. Try and look it up. If you put in the fake answer off the internet, that means you cheated. Don't do that. Okay. Just do the work. Real quickly, let's see if we can figure out what you can use for this exam. Okay. For this exam, what you want to use. Did everybody know we have a Canvas page? And we can use this page, okay? On this, so you're probably going to find this third exam somewhere over here. I'm going to make it available to you. Take-home exam. I got to readjust it. Chapter 15 and 16 is the majority of this. We have all the PowerPoints that we're dealing with on here. Right here, these are all the chapter 15 PowerPoints. If you go to chapter 15 lecture recordings in the spring of 25, notice that we have, so starting here, I started to also put it on YouTube. So if you want to, if you're more of a reading, you can get subtitles. But notice how I put chapter 15A. I don't know why this one doesn't have the chapter, but usually it tells you chapter 15C, chapter 15C. This one doesn't have it either. I guess I got lazy. Chapter 15D. You can kind of like look through and figure out what's in between, right? But it tells you which PowerPoint you're dealing with, so you can use all of these PowerPoints and all of these lectures to help you. That's chapter 15. The chapter 16 material is the same exact thing. Notice how for chapter 16 material, where is chapter 16? Chapter 16 lecture recordings. You can see we have, it tells us what section, chapter 15D. It also starts chapter 16A. This is chapter 16A. This is, and it tells you a little bit about it. Henderson-Hasselbalch equation and stoichiometry calculations. So if you're trying to do that, it shows you how to do that. Chapter 16A, stoichiometry calcs, buffer capacity, buffer effective range, titration of strong acids with strong bases. Today's section will be chapter 16B, titration of a weak acid with a strong base. So this is going to be important for this. Now, going back to this, so do we see how we figure out the pH is 3.14 from the original pH, which was done last time, where we just found the pH of the weak acid? It started at 2.37. It went up a little bit to 3.14. Do we expect the pH to go up a little bit when we titrate with strong base? Does that make sense? Yes, it does. Okay. So make sure your thing goes up in the correct order. Next thing we do, so this is what we talked about last time. This is showing us how to do 10, 12 and a half, 15, and 20 mils. Now, let's find the pH at the equivalence point. Do we all understand how to find the equivalence point of a solution? Yes? How do we do it, Cade? Okay, so you said yes, but so in this case, we have 25 mils of 0.1 molar, which is millimoles per milliliter, we can calculate how many millimoles of this there are. So 25 times 0.1, there's 2.5 millimoles of HA, which is actually HCHO2. Everybody comfortable with that? At the equivalence point, how many millimoles of OH minus do we need to add, Cade? At equivalence point, we need 2.5 millimoles of OH minus. So to figure out the equivalence point, we do 2.5 millimoles of OH minus. That's how much we need to add, right? So you could have just continued on this thing over here, but I'm breaking it up. We have the molarity of this, which is 0.100 millimoles per milliliter. Let me ask you this, Meredith. Why do I put the 0.1 millimole on the bottom here, but the 0.1 millimole on the top over there? Very good. Does everybody hear that you can put it on the top or you can put it on the bottom? It all depends on how you cancel it, right? So how many milliliters do I need? 25 divided by 0.1 is going to be how many? Is it? Oh no, it's 2.5. I was like, what the hell? 2.5 divided by 0.1 gives us 25 milliliters. So the equivalence point of this solution is how many milliliters, Bailey? And does that make sense? If you have equal molar concentrations, wouldn't you need equal volume amounts? On the exam, I'm not going to give you equal molar concentrations. I'm going to give you like one of them being 0.1, one of them being like 0.15 or something. So it's not going to be as simple, but you just follow these steps to calculate this, okay? Make your units cancel. It'll make your life easier. So at the equivalence point, it is 25 mils of added. Now, let's do a quick little learning thing. So the pH at the equivalence point is determined using the Kb of the conjugate base of the weak acid. So let's calculate the pH at the equivalence point. So as we said, 25 mils is the equivalence point. What we have to do here is we remember we had 2.5 millimoles of our acid to start. At the equivalence point, we add in the same 2.5 millimoles. So we have no more hydroxide and no more HA. But we do generate 2.5 millimoles of A minus. How would we solve for the pH at the equivalence point of this? Ricardo, remember for a strong acid, strong base last time, what was the pH at the equivalence point? Yeah. Well, when we have all of the base neutralizing all of the acid, we have no net H plus and no net OH minus. So what's the pH at the equivalent point of a strong acid and a strong base? Bryce? 7, right? And then remember I tricked you and I asked you what's the pH at the equivalence point of a weak acid and a strong base, and you said 7, which is what I wanted you to say, but I wanted us to realize it's different in this case, because in this case, when we neutralize all of the acid, we still have this 2.5 millimoles of the conjugate base. And the conjugate base of a weak acid is not pH neutral. So should the solution be acidic or basic? What do we think, Ida? If we have A minus in solution, is that a pH neutral, acidic, or basic? Take another guess. Basic, right? And that's because A minus is a weak base conjugate ion, which means it likes to stick to H plus. So in water, it grabs an H from A minus to give us a little bit of HA, but that leaves OH minus, which is straight OH minus. So it's going to be a basic solution. Okay, so we should calculate this to be a basic solution. The way that we do it, now that we know we have 2.5 millimoles of A minus, we can divide that by the total volume, which was 25 mils from the original HA plus the 25 mils from the NaOH that we added. So what is 2.5 millimole, 2.5 divided by 50? Anybody get that for me? I can tell you what it is. 0.05. It's going to be the same over there. 0.05 molar of A minus. Now, how do we calculate the pH of a weak base solution? Merve, what do we have to do? Can we use the Henderson-Hasselbalch? Can we? What's our HA? Is there any HA? We neutralized all of the HA. There is no longer any HA. So what does that mean, Kobe? If we don't have either the acid or its conjugate base, can we use the Henderson-Hasselbalch? So how would we have to solve for it? Well, that's one thing we can do. So we have the molarity of the conjugate base of the weak acid. Okay. We have to do an ice table. The ice table is seen right here. We're going to plug in 0.05 molar minus x, 0, 0, plus x, plus x. Remember this? Have we ever done an ice table in this class? Maybe once or twice, right? We solve for this. We make x negligible. Oh, so but in this case, this is a KB expression, right? The base grabs the water to make OH minus, so we have to find KB. I'm not going to give you KB of the conjugate base of the weak acid. How would we solve for that? Kayla? We have the Ka. The Ka was given in the problem, or we could have looked it up. The Ka is 1.8 times 10 to the negative 4. Does everybody remember Ka times Kb equals Kw? So if we want to find Kb, Kb equals Kw divided by Ka. So we do what is Kw? 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5. That means the Kb for this conjugate base is 5.6 times 10 to the negative 11. We plug that in here. We have our x squared from the two x's on the ice table. The 0.0, why is this 0.05 and not 0.05 minus x? Nana? Why is this 0.05 and not 0.05 minus x? Right here. Is this KB value a large value or a small value? Super small. So it's not really going to generate, it's not going to lose that much in this part over here, 0.5 minus x. So we make x negligible. The x's are gligible. I don't know if that's the word, but whatever, not negligible. They're not negligible. So we solve for x. That gives us the OH minus concentration. We can find the negative log of that to find the POH and do 14 minus, and that gives us so is that a slightly basic pH? Yes? Is that what we wanted? Yes, we feel confident about it, okay? So once again, there's a lot of ways to do this. You do it however you want. You show your work on the exam, okay? You're going to put in all your answers, but I'm going to have one problem at the end where it says, take a picture of all of your notes and put it in there, okay? Somebody asked me in lab, oh, I have like 2 graphs and my report that I have to write. How can I put it in one file? Is there anybody in here who could give advice for that? How could you do that? Bryce? Just add it to the doc. Take the picture of the graph, put it on the document, and now you have it all in one document. Or make a PDF of it. If you don't know how to do that, what should you do? Do you have to go pay $1 million to someone to figure that out? Do you have to put in $50 into the internet to ask the internet how to make a PDF out of a figure? No. Use the internet, okay? Internet helps you with everything.
There's an app that's called Genius Scan that has an ability to like transfer documents from your Google Docs into PDFs or like add images to Google Docs or
Are you
make
hearing
image
this?
PDFs. It's called
Thank,
Genius Scan.
thank you, Emma. Genius Scan. So basically, not scan. Genius Scan, okay? Or there's like 700 other different things you can use. Emma gets paid for every person she gets on there, so that's why she's touting that. But get her some NIL money or whatever it is. I kind of only know what that is. I make up stuff. So do we know how to calculate the pH at the equivalence point? So at the beginning, to find the pH of the weak acid, it's pH of a weak acid. At the equivalence point, it's finding the pH of a weak base. In between, it's finding the pH of a buffer. Are those all the kind of concepts that we wanted to learn for this? Pretty much, right? So for this problem here, so the initial, I'm gonna just show you. So this goes through how to do it, finding the weak acid. This is just finding the pH of a weak acid, okay? So I'm not gonna spend any time showing you this, but the notes are on here like that, okay? Before the equivalence point, this is where we use the Henderson-Hasselbalch. We have to use stoichiometry to determine how much of the weak acid got neutralized. Whatever you neutralize of the weak acid, it generates that much of its conjugate base. Use those ratios in the Henderson-Hasselbalch. Now, so that's the stoichiometry part over here in red, and then you can just use this part over here is the Henderson-Hasselbalch equation part. So there's a couple steps to it, but it just shows me you understand how to do that. Now, this for C, I'm going to ask you about the half equivalence point. So let's do this problem. The half equivalence point. So at the equivalence point, the number of moles of HA equals the number of moles of OH minus added. Is everybody comfortable with that explanation? Yes? So that's why we had to find the pH of the weak base that is left over, because all of the HA is converted into A minus. So it's just finding the pH of the weak base solution. The big difference is we have to think about the dilution factor. What happens at the half equivalence point? Anybody want to take this? Rebecca, what happens? Let's think about it. At the equivalence point, all of the HA is converted into A minus. At the half equivalence point, what happens? Janessa, what happens at the half equivalence point? If there is 100 people in here on this left side of the room, and they all have hats, and I bring in 100 people at the equivalence point to take away all those hats, what happens to those 100 people who had hats? They now no longer have hats, right? What happens if we have 100 people, and at the half equivalence point, how many people come in and take the hats, Robert? There's 100 people, and half of them get their hats taken. So now we have 50 people who have taken the hats, and there's 50 people. So there's 50 people who lost their hat and 50 people with hats. So what situation is this, Jackson? At the half equivalence point, what's happening? So let's just arbitrarily say we had 100 HAs. At the half equivalence point, we're down to 50 HAs, but the 50 that lost their hats or got deprotonated become 50 A minuses. Is this a special situation that we know about, Riley? What happens when HA is equal to A minus? What happens to this thing right here? Colby? Not quite equilibrium, but it means that the numbers are equal, 50 and 50. What is 50 divided by 50? And what is the log of 1? So the pH equals the pKa at the half equivalence every time. If we have 60 HAs at the half equilibrium point, at the half equivalence point, how many of them are going to be deprotonated? Bryce? 30. So now we have 30 HAs left and we have 30 deprotonated. The ratio is the same. So can we make the stark thought? So those of us who like to make flashcards, what can we always say at the half equivalence point? Nana. Let me color code what I want you to know. What happens at the half equivalence point? Everybody hear that? the pH at the half equivalence point of a weak acid strong base titration will always equal the pKa of that weak acid. So instead, you could go through and do all the work and do all of the ice tables or Henderson-Hasselbalch and stoichiometry. But if there's a question that asks, what is, so like in this problem over here, if this was the take-home exam, at the half equivalence point, all you have to do is be like, okay, I know pH equals pKa here. Find the Ka, take the negative log of it. That's going to be the pH of the solution. Does that make sense? And it also gives us a idea of how much it is. Okay. So let me show you the old take-home exam that I had prepped, but I'm going to change it a little bit because someone might know someone from the past. Some of you are social little butterflies, which is why you don't show up to class on Friday. Let's see, take-home exam for those. So let's look at this exam. Lionel Messi, anybody know who that is? Performs a titration using an unknown weak acid with the Ka of this. He starts with 10 mils of 0.250 molar HX and titrates it with 0.175 molar potassium hydroxide. Ooh, what a tough one. What's the difference between potassium hydroxide and sodium hydroxide? Anybody know? Absolutely nothing. Na plus, we say always dissolves. K plus also always dissolves, okay? So what volume of KOH needs to be done to reach the equivalence point? Everybody know how to do that? Yes? You think I could do this whole thing in 7 minutes? It'd be fast, okay? So for this problem, what is so this is just, so I'll tell you how to do this one, because if you don't do this one, it's gonna suck. You do 10 mils of HX, and we multiply it by the molarity of 0.250 millimoles per milliliter, and this is HX. 1 millimole of HX neutralizes 1 millimole of OH minus. That's assuming it's 1-to-1 stoichiometry. Should I give you a hard one and put 2-to-1 stoichiometry? No, I want everyone to do good because I hate giving partial credit. Actually, I'm not even giving partial credit on this. So do it right because you got a full 5 days to take this test, okay? Now, do we know the molarity of the OH minus? It is 0.175 millimoles of OH minus per milliliter. 10, is it 10? Yeah, 10 times 0.25 divided by 0.175. If we do this, should it be more or less than 10 milliliters? What do you think, Ian? Should it be bigger or larger? If we're using 0.25 molar acid and we're using a weaker base, do we need more weak base or less weak base to neutralize it? More. So did anybody punch this into their calculator? I only put this up there. What'd you get, Robert? Okay, 14.3 milliliters. So is that higher than the 10 mils? Yes, that makes sense, right? So now we know what the volume is. So then I ask what volume of KOH needs to be added to reach the equivalence point? What volume of KOH needs to be added to reach the half equivalence point? How would you figure out the half equivalence point in this case? Let's see. Bianca, how would you figure out the half equivalence point? You take the equivalence point and times it by 0.5 or divide it by 2, whichever one you want to do, right? That's giving you half. That's going to give you that. What is the pH before any addition? This would be solving for pH of weak acid with a molarity of 0.250 molar HX. I give you the Ka of that, so you would use that to solve for that. Everyone comfortable with that? Okay. What is the pH after 2.5 millimoles of KOH is added? So going back to this problem, we had 10 mils of 2.5 molar, so it was 2.5 millimoles per milliliter. So maybe you should just solve for this separately instead of doing it all in one like I did the other one. This tells us we have 2 or 25, 10 mils times 0.25 molar. No, it's 0.25, sorry, 2.25. So 10 times 0.25 is 2.5 millimoles of HX. Does that seem right? So we have 2.5 millimoles to start with. So when we do, so for this 2.5 mils added, it's a stoichiometry problem. Our HX is 2.5 millimoles, and we're adding 2.5 milliliters of what was the KOH solution? 0.175. This was 0.175 millimoles per milliliter. So anybody got 2.5 times 0.175? Hmm? 0.4375 millimoles of OH minus added. We subtract 0.4375 millimoles. That leaves us with 2.0625 millimoles of HA left. But it also added 0.4375 millimoles of A minus. What can we use to solve for this part of the equation now, Colby? So we have some HA and we have some A minus. When we have both of these things, what should we do? Abby? Henderson, Hasselbach, or you can generate an ice table. So you would do that for that one. This value should be lower than the pKa, right? Because you haven't added enough to reach the pKa. When 9 mils is added, what did we say was the half? I think it was like half of 14, so 7. Notice I also asked, like, what is the POH at the half equivalence point? So it's kind of a tricky one, right? I didn't ask for the pH. I asked for the POH. So if you use pH equals pKa, that's not going to give us the POH. That's going to give us the pH. Then we got to do 14 minus pH to get the POH. So read the question. Don't be a robot. Think about what you're doing. What is the pH at the equivalence point? That's the weak base. After beyond the equivalence point, it's just excess OH minus, and we did that last class. That's how you would do that one. I'll probably put some questions like this. Is this solution acidic or basic? What do you think, Bryce? So you have to break it up into the ions, Cu plus and NO3 minus. Are either of these pH neutral? Anybody? Are either of these pH neutral? The NO3 comes from nitric acid. Is that a strong acid, Ricardo? You got the list? Is that a strong acid? So that means that this is pH neutral. Is Cu plus coming from a strong base? No. That means it is going to be acidic. Okay. So this was from the end of chapter 15. So you have to think about that. If we know that metals that are not from the strong bases, they're all acidic, we would say that that is acidic right there. What about KNO2? How would we do this one, Cade? Break that apart into two things, K plus and NO2 minus. Are either of those pH neutral? Guess again. Yes, which one? K plus comes from KOH, which is a strong base. Do you think for this test, it might be good to know the strong acids and strong bases? Only if you want to be successful, okay? You don't need to know it. NO2 minus, does that come from a strong acid, Alondra? The only strong acid that has a polyatomic ion is NO3. That's not NO3, so that must be a conjugate to a weak acid, which is basic. So you would say that this is basic. Everybody see that? Ca2 plus and Cl minus. What about this one? What do we think? Ray? Is Ca2 plus pH neutral, acidic, or basic? Guess again. Guess again. Very good. Cl minus. Guess. Guess again. Guess again. We eventually get there, right? So they're both pH neutral. So what is it? Acidic, basic, or neutral, Ian? They're both pH neutral. Would it be acidic, basic, or neutral? Neutral. Very good. So that would be neutral. That's how we do that. Sorry I took you an extra minute again. My son's gonna be so mad at me.